Howdy. So we're looking at practice quizzes for Chapter 11. So this is going to have a bunch of molarity, molality calculations. The formulas are given in the notes. The calculations aren't too bad. Just make sure that you're paying attention when we have the mole fraction. It has to be the moles of everything on the bottom, not just the moles of what we're interested in. So it's what we're interested in divided by the total. Molality is a little bit weird. It's got that italics in for the symbol. It is kilograms of solvent on the bottom, whereas the rest of them are all talking about solution on the bottom or the total. So it's a little strange. So I'll let you do those calculations. Not too bad. Then I'm going to look at practice quiz 6. And here we're looking at our solubility. And so we're really looking at whether things are polar or non-polar. So water is polar, it does hydrogen bonding. Carbon tetrachloride, even though it has polar bonds, its shape as a tetrahedral is going to not lead to a separation of charges. And so carbon tetrachloride is non-polar. And so we're going to expect things that are ionic to go into water, things that are polar to go into water. CO2, be careful, is actually non-polar when we draw it out. CH2 has got a carbonyl, it's very polar, so let's see if I can draw the basics of it for us. And so it's got carbon oxygen. That's a wonderful straight line, right? But this is my partial negative, and here's my partial positive. And I can draw a line and separate those charges. So this will go into water really well. It also can accept hydrogen bonding, even though it doesn't normally do hydrogen bonding itself. All right, IMF overwhelms. We're looking for here one hydroxy group, one OH. We'll get 6 carbons to go into water. Be careful, there's a carbon at every intersection here. And so this actually has quite a few carbons and one OH. And so this is dominated by the nonpolar section, which would be hydrophobic. And then we have the hydrophilic section here, which is going to be our polar section, and also does hydrogen bonding. So this one we expect to go into fat soluble because it's mostly non-polar. Whereas if I look at the next one, it's got all these OHs, way more OHs than for the number of carbons. So 1, 2, 3, 4, 5, 6 carbons. And remember, 1 OH is enough to handle 6 carbons. So we've got plenty of carbons. So this is going to be dominated by hydrogen bonding, which is OHs. And so this will go into water, and fat soluble will be just picking on it. So then we have 7, Raoult's law. So 2 different formulas for Raoult's law. One where we have a non-volatile solvent. We're just comparing if it was a pure solvent, its new pressure would be the same as its standard pressure. And so the reason why they pick 25 degrees Celsius often is that's the standard conditions for a lot of these. That's used to be called room temperature. It's about 77 degrees Celsius. Sorry, 77 degrees Fahrenheit. So this one, we're going to take our grams of ethanol and our grams of glycerin, and I'm going to use these and find the molar mass, and then I'll get the number of moles of my ethanol and divide it by the overall total number of moles. And once I do that, I can multiply that by this 136, and that's how I'll get the vapor pressure of my solution. I do pentane and hexane. I've got to worry about these being, so I want to say this one here was like 3.5-ish for the total moles. Down here I'm looking at 511 and 150 torr, and when we go through this, I've got 0.2 moles of the pentane and 0.3 of the hexane, so about 0.5, almost 0.6 moles total. And so when I multiply that out times my initial pressure, so it'll be if they were equal amounts, I'd have halfway between these, which would be about 300. And I actually have a little bit more of my hexane, so I expect this to be a little bit less than 300, maybe 290. Now, an ideal situation is what we see here, and that's where the solvents don't interact. The solvent and solute do not interact in the vapor phase, so the gases are not having any extra attraction. So when we're looking at that, I expect to see that ideal for nonpolar and nonpolar, or polar and polar, right? And then when I want to have non-ideal, I can have weak when it's nonpolar versus polar. So either my solvent or my solute, there's a mismatch, and so they do not want to be close to each other. They do not interact with each other. And then I can also worry about when I have unexpectedly strong, we will be introducing another IMF, particularly here we're looking at hydrogen bonding. So if one of my compounds does hydrogen bonding and the other doesn't, but when I mix them, they're able to hydrogen bond to each other. For instance, when we're looking at water and acetone. So we will show you these diagrams and ask you to compare them. So the straight line for going from the pure compound to the other pure compound, if that's a straight line, that's ideal. So Y is ideal, and we would expect that when we have polar with polar and nonpolar with nonpolar. Now, here I've got the vapor pressure lower. That means I have stronger IMFs, and so this introduces a new IMF, so hydrogen bonding. So this will be something that introduces hydrogen bonding that's not present in both of them. And over here I have unexpectedly weak interaction. So the vapor pressure is higher than we expect it to be. And so that means that these aren't really wanting to mix. They're really not wanting to attract each other. And so that's when we have a polar and a non-polar solute and solvent. So the first one up, I've got all carbons and hydrogens. So this is London dispersion and London dispersion with nonpolar and nonpolar. So I expect that to be an ideal solution. And B, I have nonpolar with polar, and so I expect that to be a weak interaction, and so that's going to be Z. And they didn't ask about it, but usually our example is acetone with water to give us when it's unexpectedly strong. So be careful. The strong stuff means that this curves up, weak means it curves down. Nope, other way around. Strong means it curves down, weak means it curves up. And so when it's weak, the vapor pressure is higher than the ideal. So then we're going to switch over to our depression. And so when we make a solution, we're going to be lowering the vapor pressure. Okay, so boiling point elevation is also caused by vapor pressure depression. And so keep in mind the boiling point is when the vapor pressure equals the atmospheric pressure. And so if we lower the vapor pressure, we've got to raise the temperature to get to make it equal to that atmospheric pressure. We also have to worry about the freezing point depression or melting point depression. That's the same. Okay. So let's see. First off, we've got Van 't Hoff factors. This has the symbol lowercase I. And so I'll have one for sodium, one for chlorine. So we're just looking for the number of particles. So calcium is a +2, chlorine, each one of those is a -1. So I have 3 total particles here. This is sugar, and it is only going to be 1. It's all covalent. So just remember, anything that's soluble in water and ionic will dissociate. Be careful about polyatomic ions. So you might review some of those. Just be careful. Boiling point and freezing point. So this one looks like it's going to be difficult, but what we're going to do is we're going to define the boiling point for our solution here, and it's water. So I expect this to go up by the delta T with the boiling, and then so it'll go above 100, and then we're going to start at 0 Celsius, and we're going to go down by the delta T. So I'm going to take 0 and subtract delta T to get my delta T for my freezing point depression. So the delta T for each of these is going to be I times the molality times the delta H, whichever one you want to use. So not too bad. The only kind of sneaky part here is you have to remember to subtract for the freezing point depression and to add for the boiling point elevation. So I'll let you do that math and do that. And then last one here is osmolarity, and we're just going to take the Van Hoff factor and we're going to multiply it by the concentration. So here I've got molarity is 1, Van Hoff factor of 2. I should have an osmolarity of 2. So here I have 0.5, and the Van Hoff factor is 3, so 1.5 molar. And sodium phosphate, I've got an I of 4, and so 4 times 8 is 0.25 times 4 gives me an osmolarity of 1. All right. Hypertonic means the solution is more concentrated. It has a higher osmolarity than inside my container or bag or cell. And so when we're looking at this, we're always looking at whatever is on the outside. So the water will be flowing into the bag if it's the inside of the bag is more concentrated than the outside. If they're the same, it'll flow in and out. Okay? And so we'll give you a picture and ask you to identify which way the water will go. It'll either be going both out or both in, or one in and one out. One in, one out will be isotonic when they're the same. Hyper is when the outside is more, and so the water will be going from the inside towards the out. And then hypotonic is less, and so it'll be going from the outside. The water will go in to try and lower the inside concentration. So as I look here, I've got these that look very similar, but keep in mind I've got an osmolarity of 2 inside, and the outside I have 4. And so this will be wanting to go towards the higher osmolarity. And so it'll go out, and that will cause my bag to shrink. All right, so I'll be coming out. This one I've got 2 on the inside and 1 on the outside. So this one, the water is going to go in to try and dilute this bag. So it'll go through my semi-permeable membrane. This leads to the cell, the bag potentially popping. This one, 9 on the outside and 1 on the inside. We might call that isotonic, or we could just the inside, if they're asking for it, we could even say it's hypotonic. The water will go in. I'm looking for my red blood cells. I don't see any of those drawings, but we also have the same situation with red blood cells, and so I'm going to draw 3 of my red blood cells, and we'll kind of discuss it real quick. So if the solution on the outside is more concentrated, the water will come out. So more concentrated here, I'm looking at hyper. Right? And if this comes out so much that it shrivels up, we can say the cell has crenated, so it has shriveled and potentially died. We're mostly looking at red blood cells in our examples, and so when it shrivels up, it's no longer doing its job. When it's ISO, the inside and the outside are the same, and so we have some going in, some water going in, and some coming out, and it will assume its normal shape. And so the shape of red blood cells is very different. And then if we have the outside solution is hypotonic, then the water will go in because it's more concentrated on the inside. Right? And so if the water all goes in at once, it might burst, and we call that lysis. Shows it dies off. All right. And so we'll ask you which way the water flows. Is it isotonic, hypertonic, hypotonic? Is it going to crenate? Is it going to lyse? Those kind of things. Excellent.